This module introduces the hypothesis test, an important statistical tool. And in this video, we'll be looking at the computations involved in obtaining a test statistic and a p-value. You'll recall that a hypothesis test was a 6-step process. 6 steps that we intuitively really already knew before we ever walked into a statistics classroom. But the 4th step in that process, obtaining the test statistic and p-value, is something that we intuitively knew about but need some technical detail on. And that's our focus in this video. How explicitly do we come up with that test statistic and p-value? Let's work through an example. Let's suppose we've tossed that coin 100 times and get 63 heads and 37 tails. We would like to know 2 things. The first is the test statistic, a measurement of how far 6337 is from that 50-50 we expected. The other thing we want is a p-value, a probability. What's the chance of getting 6337 from a fair coin? How do we compute these things? Well, let's draw a picture. Always draw a picture. Why do we draw this picture? Because it's stats class, Dr. Asp. We draw bell curves in stats class. Why do we draw bell curves in stats class? Our friend, the central limit theorem. You'll recall from our module on sampling distributions that with a large enough sample size, the distribution of possible aggregate values will follow a bell curve. In this particular example, 50% fair 50-50 split on 100 tosses is the most likely possibility, and we'd like to know the chances associated with a 63-37 split. Now, understand, if 63 heads means the coin is not fair, then 64 heads means that as well, and 65 heads, and 66 heads, and so on. We're looking for this entire area out here, not the chance of exactly 63 heads. But wait, there's more. If 63 heads, 37 tails means a funny coin, then 37 heads, 63 tails means a funny coin as well. So we're actually concerned with both of these red shaded areas from our data on out in either direction. How do we find that area under a curve? It's easier to work with the lower tail. We know that a z-score is observed minus expected over standard deviation. In this case, we observed 37%. We expect 50-50. And since this number right here is a proportion, we want the standard deviation for a proportion, which we saw in our module on sampling distributions, was p times 1 minus p over n, square rooted. Okay, do we use 0.37 for p, or do we use 0.5 for p? It's a good question. I'm glad you asked it. We use the 0.5. Why? Remember what we're asking here. We're saying if the coin is fair, could we get 63 heads, 37 tails? So if the coin is fair, there will be this much variability in a set of 100 coin tosses. compute this z-score, we get minus 2.6. In other words, this point right here is 2.6 standard deviations below the mean, and this point here is 2.6 standard deviations above the mean. This is our test statistic. To turn it into a probability, this function in Excel will give us the lower tail area. This upper area will be the same, so we simply double it. Our p-value is twice this lower tail. Our p-value is 0.00932. Let's work another example. Suppose we got 54 heads, 46 tails. Again, what is the test statistic? What is the p-value? I'll ask you to take a minute and work these out. Pause the video here, work them out. When you've got a solution, start the video again to check your answers. Here we go. We got 54 heads and 46 tails, so we want the area from 54 on up. If 54 heads or more means a ungood coin, then something just as much off in the opposite direction is also a problem. Things could go awry in either direction. 46 minus the 0.5 that we expect, p times 1 minus p over our sample size. This point is 0.8 standard deviations below average. This point will be 0.8 standard deviations above average. Norma.s.dist function gives us this area being 0.212. Total red area will be double that. Our p-value is 0.424. Here's a table of some other possible outcomes. If you're still shaky on computations, you might pause the video here and see if you can get one or two more of these results. But I'll go ahead and focus on what this table is telling us. Basically, we're looking at a set of possible outcomes we could have gotten. These are some of the possible outcomes, the test statistic associated with it, and the p-value. In other words, could we get 99 heads and 1 tail on a fair coin? Well, that outcome is 9.8 standard deviations away from what is expected. The chance of that happening is virtually 0. We worked through this one earlier in this video, and you just did this one as your computational example. Now remember, we've already decided that 99.1, that's not a fair coin. 51.49, yeah, we were willing to believe that was a fair coin. In jargon terms, we would not reject the null hypothesis down in here, around 51.49. Our test statistic is small. We are pretty close to what we expect. The p-value, the chance of that happening is pretty large. On the other hand, we would reject the null hypothesis up in here, 99.1. That's a long ways away from what we expected to get. The test statistic is big. The chance of that happening, the p-value, is small. And the question was, where's the boundary line between rejecting the null hypothesis and not rejecting the null hypothesis? In other words, how big is big? How small is small? It's an excellent question. I'm glad you asked that. The answer is, by tradition, p-values of 5% or less are small, and we will reject the null hypothesis. Whereas p-values larger than that are big p-values, and we don't reject. Notice where the line is drawn. 60-40, 2 standard deviations away, that p-value is less than 5%. These results up in here will cause us to reject the null hypothesis and conclude that the coin is not fair. Whereas these results down here, the probability is larger than our traditional 5% value, and so we are not rejecting the null hypothesis. Again, that 5% value has no basis other than tradition. But for right now, I will ask you to be traditional. Use 5% as the boundary between rejecting the null and not rejecting the null hypothesis. So in conclusion, notice what we've done. We've used the central limit theorem to allow us to draw a bell curve. And on the basis of that bell curve, we can find a test statistic, and from that, a p-value. If that p-value is small, we will reject our null hypothesis. If that p-value is big, we will not reject the null hypothesis. And that's the basic computational mechanics underlying the hypothesis test. If we are rejecting the null, remember, we don't want to draw a conclusion about hypotheses. We want to draw a conclusion about the coins or whatever it is that we're testing. If we're rejecting, we're saying, yes, we have enough evidence. If we're not rejecting, we're saying, no, things are inconclusive at this point. We'll continue to believe the coin is fair because we haven't proven it otherwise.